and running. So here we go. I don't know what that is, but it looks good. Okay, so we are recording. And again, for those of you that were trying to keep up with my narration, our essential questions are: what makes a function linear? How do I find the average rate of change? And how do I graph linear functions and other linear relations? I had to make myself a little note to remember to press record. Okay. So first, what I have here is a definition for what is a linear function. So we're going to fill that out. A linear function is a function that is defined by a relationship between input values, or your x's. Those are your independent values. You can pick whichever x you want. And your output values, which are your y's. They are the dependent values, where the change in inputs and outputs are both constant, which creates a slope, a straight slope. Okay, the change in inputs and change in outputs are both constant, and the set of points found will create a line on a coordinate plane. They have a linear relationship. Okay, they have a linear relationship. Okay, guys, I'm going to check my Apple Pencil real quick just to make sure that it is got enough juice. 23%. We'll probably get there. Okay, so let's talk about, I'm going to give you a table of values here. Okay, so let's take a look at this table of values. Let's zoom in here. So this is a graph of a linear function. You can tell it's a linear function because the points graphed create a line, right? But the definition of the function is that the change in x and the change in y remain constant. So if you look at this here, as we go from one x to the next, it's a constant change of 10. And on your y's, it's a constant change of 50. Okay, so that's their relationship. For every 50 you go up, you go 10 over. And so the equation of this line with a rise of 50 and a run of 10 with a y-intercept of 0 would be the equation y equals 5x. And so you can see that there's a linear relationship between those numbers. So basically this means for every 5 we rise, we run 1. That's what that means, okay? So it has a linear relationship. Versus over here, if we look at this function, you can see that maybe it's parabolic, maybe it's exponential. We would have to do a little math to determine that. But since x is independent, you can see it's going up 10, up 10, up 10. I can decide to go up 1, 1, 1, 5, 5, 5, whatever I want. But as I'm going up in this constant step of 10, going to the right 10, my change in y changes. I'm sorry about that. Okay, you can see it goes up 20, then it goes up 40, then it goes up 60. That's not a constant change in y. And so this does not create a linear relationship. It's a different type of function. So the criteria that creates a linear function is that a constant change in x produces a constant change in y. So first, let's go to the pear deck. So go ahead and go to the pear deck, and we're going to do a problem. So I'm going to start the class, and we are going to answer the question. Using the table of values, answer the questions. Just highlight yes or no. Is the change in inputs or x the same? Yes or no. Is the change in outputs y the same? Yes or no. And if that's the case, is the function linear? So 7 of you have responded. Where you guys are going now. Okay, give you another 10 seconds or so. Okay. All right, so go back to your Google Meet and let's take a look at your responses. All right. So I can see here. Can you guys see what's happening? I hope I didn't hit share. Let me share. There we go. Okay, so we can see here that this person said, yes, the change in X's were the same, up 1, up 1, up 1. Yes, the outputs were the same, up 3, up 3, up 3. And so, yes, the function is linear. And we can just kind of, zoom through here. And I guess we got that concept down. So there'll be a couple problems on your assignment today. Okay, here we have a no. Is the change in outputs Y the same? I'm wondering why we chose no. It's up 3, up 3, up 3, up 3, up 3, up 3. So yes, they are the same. Okay, so we have another one up no. So I really would like to know why that was a choice. Because if this is our answer, yes, the change in X's is the same, but the change in Y is not the same, then you could not say that this function is linear. These two things have to be, outputs, input changes have to be constant in order for it to be a linear function. So be careful with that. Okay, so let's go back to notes here. And I'll share the screen. And let's go back to our notes. Okay, so we're looking at the functions y equals mx plus b, okay? If we have y to the first equals x to the first, regardless of what values are there, you know, you could have a 2 here and a 5 here and a plus 7. That doesn't matter. As long as it's x to the first, y to the first, there's going to be a linear relationship between your inputs and your outputs. Okay, so let's talk about some specialized linear functions. We're going to start off with the identity function. And the identity function just basically means whatever I get on the left, I get on the right. And usually when we're graphing the identity function, it's going to cross the graph at 1, 1, 0, 0, 2, 2, negative 1, negative 1, negative 2, negative 2. Okay, the identity function says that y equals x. They are identical to each other. Whatever x is, y is identical. Okay, so this is what we call our identity function. It has a slope of 1. So f of x equals x is one way to look at it. Y equals x is another way to look at it. It has a slope of 1 and a y-intercept of 0. And this is your identity function. Okay. The next function here is a constant function. Okay, a constant function looks like this. It's linear. It is a function. It's just horizontal. Constant function has the equation f of x equals some number b, b being your y-intercept. Okay, and in this case, your slope is 0. Okay, it's a 0 slope. That's because it has no rise. It only has run. So that's 0 over any value, doesn't matter. 0 divided by anything is 0. So it's where the function remains constant. It just stays flat. Sometimes this equation can look like this, y equals 0x plus b, so that you can see, regardless of what 0x you plug in, you're going to multiply that times 0, and it's going to zero out your x. So there's your constant function. Now this next one is not a function, but it is a line. So we're going to do a vertical line here. I'm going to put a point right there at A. Okay, this is not a function. It fails the vertical line test, so it's not a function. Okay, this is a vertical line. Okay, and so the equation for this is x equals A. Notice it doesn't have a y-intercept in this case, or it could look like this, x equals 0y plus A. Okay, and when it's solved for x instead of y, then it's run over rise versus rise over run. But anyway, here, your slope is undefined. Because this one has rise, but no run. It rises, but it doesn't run. So that means whatever your rise is doesn't matter because you're dividing by 0 and that's undefined. Okay. So I think that you may remember these maybe from Algebra 1 or something, these two acronyms. Horizontal is a 0 slope, y equals. Vertical is an undefined slope and it's x equals. So if those things, if you needed those to remember that information, then there's that. Okay, then you have, so those are your specialized lines. You have your identity function, your constant function, that's just a 0 slope, and then your undefined slope, which is not a function, but it is linear. Next, we have a positive line or a positive slope. Okay, so that just means that your slope is greater than 0. Your slope is greater than 0. And there's a positive correlation. I'm just going to put a plus sign, a positive correlation between your x and y values. So in calculus, what we would say is this: as x gets larger, infinitely large, y also gets infinitely large. So the bigger the x, the bigger the y. Okay, that's a positive correlation. It's like the more you eat, the more you weigh. That's a positive correlation, right? Versus maybe the more you run, the less you weigh. Maybe that would be a negative correlation. Okay, so you also have your negative slope, which would be a line that is dropping. So this would be m is less than 0. Your slope is less than 0. And that is a negative correlation between x and y. And in calculus, we would say as x approaches infinitely large values, our y would approach infinitely small values. So the bigger the x, the smaller the y. They don't have a positive relationship. Okay. For slopes, just let's go back to positive here. A slope could look like this. It could be a positive over a positive, or it could be a negative over a negative. Just simple little reminders here. Whereas a negative slope, you have options of a negative divided by a positive or a positive divided by a negative. Just little reminders, which is useful sometimes when you're graphing, especially negatives. Well, especially when you're having to graph a slope and your y-intercept's really high on your graph and you can't go up and to the right, so you go down and to the left. So it's important to remember that. Okay, so those are just your reminders for that. Let's talk about the formula for slope. If I give you the points, you're always looking, when you're finding slope, you're just looking for the rise and the run between 2 points. So if I give you 2 points like this, x sub 1, y sub 1, and x sub 2, y sub 2, and let's say I give you a line like this, and we'll put a point here and a point here, and this will be x sub 1, y sub 1, and this will be x sub 2, y sub 2. Remember that your slope is just your rise over your run, right? So this would be your y sub 2 minus y sub 1. That's your rise. That's your change in y over your x sub 2 minus x sub 1. And that's your run. So you're always doing rise over run. Rise alphabetically comes before run. So rise comes first, run comes second. Also think about it. If you're going to run, first you got to stand up. You got to rise before you run. Okay, so remember that. Formulas for slope. My preference is not rise over run, is not y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or y sub 1 minus y sub 2 over x sub 1 minus x sub 2, because you can also do that. My preference is change in y over change in x. Delta y over delta x. By the way, this is not okay. Y sub 2 minus y sub 1 over x sub 1 minus x sub 2. That is not okay. That will throw off the type of slope that you should be drawing. If you need a positive slope, you're going to find a negative. If you need a negative, you're going to find a positive. So be very strategic and careful. So those are your formulas for slope. Again, my preference is the simple one, change in y over change in x. Okay, average rate of change. Now here we're going to start talking about, you use linear equations happen a lot in calculus, like a lot. You're finding the point of a line that's tangent to a curve, and that requires you to use the slope at a point. Average rate of change, so it's always about slope here. Here's what it is. Average rate of change is just the slope between 2 points. And those points can be on a curve. They can be on a set of data, on a scatter plot. Slope between 2 points. But here's the key. When I'm finding the average rate of change, I want to know how much it changed per unit, like how much is miles per gallon or miles per hour. So I want my denominator to be simplified to 1. So it's a slope between 2 points that is simplified when the denominator equals 1 unit, whatever that unit is. Like, for example, hours or minutes, 1 minute, 1 hour, 1 whatever that unit is, okay? So when we're finding average rate of change, that's what we're looking for. Okay, so let's take a look at just a little quick refreshers on graphing lines. Okay, so here we have determine the slope if it exists. I identify if the line is a function and graph the following lines. So we'll start off with A. Excuse me. And we'll do this one, I'll do it in red. Okay, so here we have f of x equals negative 2/3 x plus 1. That looks a lot like y equals mx plus b to me. So here's my slope, negative 2/3. My y-intercept is when I plug in 0 for my x. So that would be 0, 1. Y-intercept, you can answer it's just 1 because it does say y-intercept, meaning it's intersecting the y-axis. So let's graph that. So when you graph a line, remember that you have to start with a point before you can graph its slope. What's the relationship between the x's and y's? So 0, 1, and then you have a slope of negative 2/3. So that means I can go down 2 and run 3 to the right, or I can go up 2 and run 3 to the left, right? Because that can be negative 2 over 3 or 2 over negative 3. Both of those are negative. Graph our line. and label it A. So there's A. Is it a function? Yes. Okay, here we have the next one. I'll go to blue. It says x equals -2. So here's what I know. X equals -2 plus 0 y's. There are no y's in that equation. So if I were to do a table of values, in this case, because it's solved for x, my y would be my independent variable. So I could pick values for y like -1, 0, and 1. And I could plug those in. -1, 0 times -1 is 0, and 0 plus -2 is -2. If I plug in a 0, it's x is still -2. Guess what x always equals? It always equals -2. Doesn't matter what y is. So it would be that line right there. So what is my slope? It's undefined. My x-intercept is -2 or at -2, 0. And this is not a function because it doesn't pass the vertical line test. Okay? So just reminders, when you have x equals a constant, it's a vertical line. So that's B. Okay, moving on to C. We'll do that in green. So it says y equals 5/2. Well, it's kind of like this. Y equals 0, x's plus 5/2. So you can see your slope there. This is a 0 slope. So this is a constant function. It's flat. It doesn't rise. It only runs. Okay, your y-intercept is 0, 5/2 or just 5/2. So let's graph that. If we have at 5.5 our y-intercept and our slope is 0, that's definitely a function because it passes the vertical line test. And again, with this one, you could make a table of values if you forget. Whether x equals 0, 1, or -1, y always equals 5/2. It remains constantly the same. So just little reminders on how to graph. Questions? So to sum that up, in order to graph a line, you need a point and then the slope. That's what you need. You start with a point and then you graph the slope. Or you make a table of values and you start picking values and plugging them in. Okay. Now, what we're going to do is do a couple applications. So now we're starting to get into the pre-calculus of this, although I think this is pretty elementary as well because we're just using slope. So I think the key here is just to identify what is your first set of your first coordinates for your first point, what is your second pair of coordinates, okay, your ordered pairs. Okay, so it says curb ramps provide independent access to sidewalks for those who use wheelchairs. You guys see them all the time. Guidelines for the grade of a curb ramp suggest a grade between, excuse me, 5.9% and 8.3%. I want you to notice that it says the grades are in percents and to their nearest 1/10 of a percent as well. That's critical to pay attention to. That's good information. That the grades, oops, that's not a highlighter. That the grade is in percent form to the nearest 1/10. It says a federal law states that every vertical rise of 1 foot requires a horizontal run of at least 12 feet. Find the grade of the curb ramp shown below. So you see that it says that we're doing vertical rise over horizontal run. Find the grade. So we want the slope of that line, right? So we want to rise over our run. So our rise is 3 inches over our run is 42 inches. And somehow we have to figure out what grade that is as a percent to the nearest 10th. So what can we do? Any suggestions? Okay. What if I asked you to change 1/2 to 1%? What would you do? Or 1/5? Guys, it's division. So 5 goes into 1 how many times? 0 times, right? Then 2 times. So that's 0.2 times 100. That would equal 20%. 1 is 20% of 5. So when I'm asking you to give me this grade, this ramp grade, I'm just asking you to divide. So let's go ahead and pull up a calculator. Let me see if I can find one here. So we're just dividing. 3 divided by 42. That says times. How about I clean that up? 3 divided by 42. Okay, so we get 0.0714. So basically what I just did was I divided the top by 42. I divided the bottom by 42. This is what we do when we're finding rate of change. So we're getting 0.0714 inches in rise for every 1 inch in run. So that's approximately 0.714. And what we're going to do is change that to a percent, multiplying it per century, per 100. That just bounces the decimal 1, 2 times. There should be a 0 right there. 1, 2 times. Let me fix that. 1, 2. And so that would be 7.1%. And we're going to stop at 0.1 because in the answers here, or in the problem here, those percents degree of accuracy was to the nearest 10%. And so that is your grade for that specific ramp, which fits inside those restrictions. So perfect. Okay, so let me see if you really get it. Let's go back to the presentation, the Pear Deck, and let's see if you understand. Read the problem. Get your calculator out and solve. Oh my goodness. The smoke in the air is killing me. Get my calculator out here. Okay, I got 5 of you responding.
Do we round the 10th place?
Read the instructions. Give solution to the nearest 1/10 of a percent. So yes. And be careful with your rounding. So there's 9 of you. Okay, 10 more seconds to get your answer in, please. Okay, if you would go back to the Google Meet tab, let's look at the responses. So here I see 7.3%, 7.3, and then I don't know what that's, a little fun face, 7.3%. We have a 7.2%. Well, it was 7.27, and so we should round that to 7.3. Very good. 7.2, same issue there. Okay. Good job. All right. So just watch it on your rounding, please. Be careful with that. All right. So back to our notes. That was a little practice on the rate of change per 1 inch in run. Let's look at example 3. It says the number of people participating in the federal supplemental nutrition assistance program has increased from 17.12 million in 2000 to 47.6 million in 2013. So again, I would say to pay attention to that notation. 17.2 million just means 17,200,000. But I would rather do math with 17.2 and just tack million on that. Okay, so let's just take a look at this. We're increasing from 17.2 in 2000 to 47.6 into 2013. So that's a passage of 13 years, and it's gone up about 30. That looks like 30.4. Okay, it says the following graph illustrates this upward trend. And as you look at this graph, you can kind of see that it's not really linear in the graph, but we're going to look for the average rate of change in the number of people using food stamps from 2000 to 2013. So a couple things to note. First of all, the year is our x-axis, okay? So that's our run. And because we're finding average rate of time, our average rate of change, what we're looking for is per 1 year. In the rate of change, we want 1 in the denominator. So how much is it changing per year? That's a rate of change. Okay, and here we have our number of participants in the millions. And so what we're looking for here is this slope between those 2 points. Do you see? Even though we've got that curvy line, we're just looking for an average value. It's certainly not a perfect value, but this is typically how we find rate of change. So we have these 2 points here at 2000. That's your X. We were at 17.2 million. And in 2013, you were at 47.6 million, right? And so we're looking for a number of participants in the millions over, and we're looking for the change in that. So we're looking for, because we're going to use the slope to determine that. So the change in number of participants over the change in years. So that's what we're going to do. So let's set that up as 47.6 minus 17.2, y sub 2 minus y sub 1, or change in y over change in x, 2013 minus 2000. And so here's what we get, bringing it down here, 30.4 over 13. Okay, but we want average rate of change. That means that our denominator has to be 1. So what we're going to do is we're just going to divide. We want the bottom to say 1, so we're just going to divide the top and the bottom by 13. So that's 1 year. And so we'll get out our calculator again, and we'll just go 30.4 divided by 13, and that's 2.338. So we're going to go at 2.338 million. Now let's go back and talk about how we want to write that out to the degree of accuracy that the problem presented us. Notice that this says 17.2 million. That's to the nearest tenth, or 47.6 million. So we would like to go with 2.3 million per year. And that's positive, right? That's a positive change. So it was approximately going up 2.3 million per year over that 13-year span. And so we could say 2.3 million per year if we wanted to write it out as just an answer to the question, or you could leave it as a fraction, 2.3 million per year. Okay, so let's go back to the Pear Deck and do one more problem. Let's see if you get it. So what I'm seeing here, be careful. It says, using the data in the table below, find the average rate of change of the price of gasoline between 2007 and 2009. So these are your sets of data, 2007 and 2009. So let's come over here and just pay attention to, of course, you can't see what I'm doing, so let me actually present my screen so that I can circle some things. Okay, so we are looking for the slope between those 2 points. So let's come over here and take a look at how these are marked. T, that's going to be our time, right? And the cost at time, that would be your y coordinate. So T is your x coordinate, there's your independent variable, and cost at time is your dependent variable. So we're going to be using this set of points and this set of points. So what you need to do is find the slope between them to find the average rate of change. So give that a go and round to the nearest penny. We have 3 responses. Round to the nearest penny. Watch your signs. There's 7, 8 of you. Okay, that's more than half of you. Give you 20 more seconds to get that figured out. Okay, go back to your Google Meet, please. Tab. And let's take a look at your responses. So here we have negative 0.215 cents. Well, that's not to the nearest penny. The nearest penny would stop in this spot. So that 5 would make that 1 a 2. So we're not rounding correctly here. That is positive. That's saying it's going up 20 cents, going up 19 cents, going down about 22 cents. That's good. Too much move a decimal there and not a correct rounding. Okay, so let's talk about that because we weren't as successful with that as we have been on the last problem. So I'm going to go back to our Google Meet here and present. And let's see here. So here's the data that you were provided. In 2007, gas cost $2.84. And in 2009, it was $2.41. So I basically want to know how much is it going down per year. So all you're looking for is the average. So if you go, all right, so if I have $2.84 in 2007, and I'm finding its change, its average, basically, right? I'm going to subtract their numerators. So that's a difference of 43 cents over negative 2 years. Of course, I could have gone the other way. And if I divide the top by negative 2 and I divide the bottom by negative 2, well, that's going to be negative 0.215 for every 1 year. So now let's just do a little interpretation of what that means per year. How much is the price going down per year over that 2-year span? Well, when we're rounding, when we're talking money, we round to the nearest penny. So that would be that point right there. So that would be down 22 cents per year. So I'm going to just say that, down 22 cents per year. So be really careful and watch your rounding. Okay. All right, last word problem here. This one will go pretty quickly. It says increased oil productions in the United States has resulted in decreased imports. So we're producing more oil in the United States, therefore we don't have to import as much oil. Total number of barrels imported in 2008 was 3,590,000 barrels. This number has decreased, I should say has decreased to 2,810,000 barrels in 2013. Find the average rate of change. Okay, so again, we're looking for average rate of change in crude imports over the time period from 2008 to 2013. Okay, so let's take a look at the graph. The graph is really nice. Thankfully, we have a graph. Look again, your x-axis is years. Usually your x-axis is time, okay? And your y-axis is your number of barrels. So let's gather up these points here. We have this point here at 2008, which is our x, 3,590,000. Get another 0 on that. So that's 1 point. And then our other point is at 2013, and it has the corresponding value of 2,810,000 barrels. Okay, and we want to know what is the average rate of change. So how much is it going down every year? That's what we want to know. How much is it decreasing every year? So we're going to do change in barrels over change in years. So we'll plug that in. So 2,810,000 minus 3,590,000 over 2013 minus 2008, which gives us this value. That's down 780,000 barrels over a 5-year span. But I want to know how much is that per year, not per 5 years. So I'm just going to bring this down here. And let's simplify that. So we'll divide, because we're doing average rate of change, right? Rate of change. So we'll divide the bottom and the top by 5. And that's a negative 780,000. That's a negative 156,000 barrels in 1 year. So the answer to the question, find the average rate of change. So the decrease of 156,000 barrels per year from 2008 to 2013. Just remember, people, all you're doing is picking 2 points, the 2 endpoints, finding the slope between them, watching for positives and negatives, and then making sure that you're reducing your denominator down to 1 so that you can get the average rate of change, okay, over 1 unit of time or 1 unit of measure, depending on what you're practicing, okay? All right, so there's that. Now we just have these last 3 problems to do, and they won't take very long because we're just going to go back to elementary algebra here. It says find the slope and the y-intercept of the line. So we have something that looks like this, y equals mx plus b, right? So here our slope is negative 1/4. You could also write that as negative 1/4. Down 1, write 4. And your y-intercept is negative 3.8, or the coordinates 0, negative 3.8. I don't care which one you do, just be flexible and be able to go back and forth between those 2 options. For b, just solve for y, right? Just solve for y. So we'll subtract 3x and add 7 to the other side, just so that we can get it into y equals mx plus b. And solve for y. So we'll divide everything by negative 6 and simplify. So y equals 1/2 x minus 7/6. So just simplify, make sure you're simplifying. So your slope for this is 1/2, rise 1, run 2, and your b is negative 7/6, or your y-intercept is 0, negative 7/6. This feels like too simple to be teaching you or to be going over. Okay, last here is just a graph of y equals negative 2/3 x plus 4. So remember, when you're graphing a line, you have a point that you start with, and then you have the slope that you follow, the path that you follow to get to your next point. So your slope here is negative 2/3, which means that you could be going down 2 and right 3, or up 2 and left 3. That's up to you. You can make a decision about that. And your y-intercept is 4. So we start at the point 0, 4, and then we want to either go down 2 or right 3, and I think that'll work. Down 2, right 3. And there's your rise and your run. And that's pretty much all you can do because you're off the graph at that point. And there you have your graph. So today on your assignment, we'll have to do a little bit of everything that we just went over. And if you're struggling with graphing lines, you really should practice it, because I require you to graph lines all the time without me having to review how to graph them. Okay, this is pre-calculus. You should know how to graph them. All right, so that's it. So today you have the assignment 2.2a on Canvas, and you have a quiz tomorrow on 2.1. And some of you have a lot to do, because remember, you need to get all your Unit 1 stuff taken care of by tomorrow midnight so that I can get it in my grade book and push to Synergy by Friday so I can post grades for the end of the first grading period. Okay, all right. So I'm going to stop recording.